Alright, so for this one here, the form of the equation is we're going to have the same family, and it's b plus a, and we can't go any further. So if this was given an integration, and we wanted to resolve this integration, you can't do it, it's too hard. But what you can do is, if you can go backwards, if you can do the process in reverse, you can then solve this problem. And that's all partial fractions is about. You know, students get into 4 unit and they learn about partial. Ooh, we're learning about partial fractions. Ooh, well, what does it mean? Well, there it is. Big deal. Yeah, it's adding fractions backwards. Don't get upset. So where does this come in important? Now, I teach students that I've got, that I'm coaching. I'm a little bit cheeky, and I don't teach them calculus, but I teach them this. And I find that allows me to teach a Year 8 student calculus without actually teaching them calculus. And I'm not teaching them calculus in the sense of, what's differential calculus, by the way? Let's see if you remember. Come on, you're not allowed to use your mouth, but you're allowed to use your arms. Differential calculus is... Did we actually do a lesson together? Right, there's your gradients. I get whole theatres of students doing this, they all laugh. Alright? What's differential calculus about, folks? It's the gradient, m1, m2, all of that, plus or minus m. So you can have a bit of fun with it. Alright, so what we'll do here is we'll go put NDC out the front. Oh, completely messed that up. So that's step 1. Or subtract 1 would be a better way of doing it. Okay, this one here is going to be add 1. So it's just a way of getting them to do a puzzle, bit of programming. So if we do an example, what we would do is we would say a box to the power 7. So apply index to that. So we would get 7 out the front, 7 minus 1, and we would get 7 to the power 6. A very simple one. So we would have another one. Keeping the theme. Oh, now that's harder, because what the student has to do is recognise that in pre-work they have to know about indices. Now we haven't done that together yet. More than that, they have to recognise that they're going to be adding fractions. Dun, 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 dun. So this is a big deal. So what I like to try and do is to get Year 8 killing adding fractions, and this is one way to do it. So then we spend time on it. What is it? What's 1? Who can tell me what the form of 1's going to be? Ah, now we're looking at a classic adding fractions problem. Who knew something so simple could be so important? Now our kids get caught up in this. Don't kid yourselves. Our kids come to university and they struggle with this. This bit. Not this bit, not the instructions about what to do, the patterning. They get the patterning because they've been taught the shortcuts, but this is where they fail. So then we have to put it into the family. They don't like writing that step, hate writing that step, and we're back to negative a half. So we get a half, negative a half, hate writing all the lines out, or I left a line out there. Okay, so doing that, and you can do the same for, I won't do it now, I'll let you do that, for code 2, which is, you recognise this as differentiation, and this one's integration. Okay, so this gymnastics is time consuming, and it's awkward, and it's difficult, and not all integrations and differentiations are polynomial based that need this gymnastics. and yet somewhere along the line students miss this, and it's the culprit. The culprit is adding fractions. That's the one that puts the sword to their ambitions. They're doing advanced maths, they start doing differentiation of polynomials, and it's adding fractions that stops them. They go and change classes then. Okay, no changing classes. I'm a big one for whoever wants to do it. First time I taught 4 unit, I got all the students together in year 11 and said, right, whoever wants to do 4 unit, go and I'll meet you tomorrow in the room, whatever it was. And the head teacher got me after and said, what are you doing? You can't do that. Because traditionally, how many 4 unit teachers did they have? One 4 unit student. Why? Oh, you're good. You're good enough. Rubbish. For me, 90% of it is you turn up. Now, there are very strong opinions in your schools about this. What I just said, people would say, can you get out of our school? Okay, that's how strong they feel about it. Mate, I'm teaching people stuff, and this is what I'm teaching them. This is how you do it. I put a 15-year-old through Maths 1, coming out of Year 9. I know what I'm talking about. Okay, that student wasn't particularly genius, but they knew this stuff from a very early age. Okay? So we don't really have an excuse, but that's the imperfect world we live in, guys. You'll get the excuses handed to you on a plate. And yes, you will find yourself nodding and agreeing with the head teacher, and you'll let it slide, and that's just part of life and our development. Alright, so for this one here, same kind of thing. So we go for, what did we say? Add 1 and divide it. Looks easy, doesn't it? So we get, looks easy. All we need to do then is to make it a little bit harder. Oops. So all of a sudden, we've got our pre-work. We're going to apply code 2 to that. We're going to go, ooh, divide by a fraction. How many guesses have you got? You could make money on that if you're going to bet your students. So half plus 1, let's go out and do that. What's the form of 1? It's a lot of work, isn't it? That's annoying. Jason, the period only goes for so many minutes. I can't, you know, I can't run the whole thing that way. 3 over 2. So we get 3 over 2, 3 over 2. This is a big problem now. Okay, a big problem. How do we do that? We've got to do more steps. Don't like writing steps. Find a way. Give them separate work. Give them separate sheets with worked examples. Give them my videos. I don't care what you do. Find a way to help them process. Because those things they don't recognise, that's what's going to cause them to fail. Not because they're stupid or incapable, you're a good teacher or a bad teacher, or they're a good student or a bad student. It's just about training. They haven't seen it before. Whoever they had in Year 9, they didn't show them. They just went from here to here. And that bit was guess it. So we don't want to be blaming the students too heavily. We want to give them every opportunity. How do we go there? I think that's probably it now. I think we'll probably turn off there and move on. Any questions about that stuff and that idea? I'll do some indices next week. Okay.
Just a comment, I've got a son in Year 7 and I'll be working with fractions with him on the weekend for a test.
Yeah, just revalue it, James. Just revalue it and make it important. You know, how do you do times? How do you do divide? The student has to recognise what's coming up. Oh, there's the trigger. There's the trigger. That's a trigger. It wants you to do something different. That's a trigger. It wants you to do something different. What's your next steps? You know, so revaluing what they're learning is what it's about. Alright, so in terms of it's not beyond them, and I've preached enough about that, and I'll get off your cases because you're gonna find that you're forced into making compromises along your journey, all in the name of grading and head teacher judgment and curriculum person know all. Okay, so let's move on. What I wanted to do was just touch base a little bit with some of the things that we did. It's only the first week, and have I started to fill your heads up? Do you feel like you've been doing a lot? I've only been doing basic stuff. Imagine what the kids feel like. Alright, so in this particular case, what we're talking about in this part of the work is integrals, and we've been looking at improper integrals. So what is it about integrals? At school we learn about definite integrals or indefinite integrals, and often students can't name them. So there's a good, I kind of tend to go quiet a little bit when the English teachers start to talk about the maths curriculum, and there's a lot of vocab and a lot of language in our subjects, and it's important that the students learn to use the words. It is important because it helps them with their memories. So if we have an indefinite integral, what does that look like? What's an indefinite integral? That's an indefinite integral, because an indefinite integral is going to give us an expression. That's the link. A definite integral is going to give us a number. And sometimes we just expect students to learn this stuff, to do the map themselves. So if we do our up and under, this will be x2 plus 1. I'll just do it as x3 over 3. The integrand is equal to x3 over 3 plus c. So there's our expression. There it is. We've gotten our expression. Our definite integral is going to require us to do the up and under. And the first thing I would do here is x 3 on 3, and then we're going between 0 and 2. And I always put by the fundamental. Now you don't have to do that, but in Maths 2 we learned the fundamental theorem of calculus. In Calculus 2 we learned about the fundamental theorem of calculus. It's a thing, okay? And the reason that I like writing it that way is because it reminds us that we have to invoke the fundamental theorem. And we're going to bomb x with 2's, and we're going to bomb it with 3's, and sometimes I'll even leave that out and just say students know that's the process. So in this case here, now you can take the 1/3 out, but if you take the 1/3 out, it's got to be across both. So I'll do both. So we could do 1/3. I have no preference. Okay, but it just means you've got to add the extras in if you keep the third out. You can leave it in and just do the bombing. So we've got 2 cubed. Actually, I said I wasn't going to use that, so I'll leave that one blank. I often do that. I'll often leave it blank. 2 cubed on 3 and 0 cubed on 3. They get in the habit pretty quickly that the second one with a 0 in it is probably going to be missing. So 2 2's are 4 2's are 8. So 8/3 units squared, and we have a number. Our definite integral gave us a number. Okay, so that should be something that we're happy with. So what is it about an improper integral, which is what we were doing this week? What is it about an improper? So if we were to go ahead and say classify these questions, well, this is shown, it's a hyperbolic sign. It doesn't matter if you don't know it, I'm happy with that. But it's cosh, it's hyperbolic cos plus c. So that's an indefinite. And this is what we get our students to do in first year who are doing analysis, classifying. Okay, y squared, dy, there's the change of programmable. They get horrified with that. They get overused to doing x's. So whenever physicists put t's and s's in, they get horrified with it, but we get that at university. So a bit of practice with different pro-numerals should be a good thing. So we'd have up and under plus c, or 1/3 y3 if we want to. and likewise it's an indefinite because it gave us an expression. Okay. Now, what is it about improper integrals? Cheeky. Now, this is a very cheeky one. So C is a cheeky one. So I'll put it up here. Now, C is being cheeky because in improper integrals, the gist of improper integrals, which is all in those notes, which is what you're supposed to come out with, is that there's two things that happen. You can either have an interval that is diverging, getting bigger, or you can have an interval on which the integrand is not defined. And what we look for is examples of that. And a simple one is you understand 1 over x. 1 over x has the geometric interpretation that around, as it approaches 0 from above and as it approaches 0 from below, it doesn't actually take on 0. In other words, you can't have 1 over 0 because in mathematics it's a profound thing. Now, when you do integration and differentiation from first principles, this is the justification for limits. Okay, now I might revisit that if you ask me to in the first part, the know-how part. So make a note of that if you want that revisited. But for our purposes here, this is an example of an interval, if we were to integrate this, where the integrand is not defined. So to do something like this makes no sense, because the integrand is not defined it's asymptotic at 0. There's an asymptote there. So what we need to do is to learn how to deal with that, which is what this week's work has been about. This particular example is a little bit cheeky in that one of the ways to step around the issue of whether or not the interval is defined is to have a function which has a limit at plus or minus infinity, whichever one's being used. So in this case here, what does e to the minus x look like? E to the minus x goes whee. There it is at 1. And down here at infinity, what's the value of the function? In the limit, it's 0. In the limit, it's 0. So what we do is we take our e to the minus x function, and the gist of what we do with improper integrals is we do this step. We define a limit, and we say that as L approaches infinity, now if this is not familiar and you need it in the know-how, let me know. Okay? And we'll do first principles and I'll rediscuss this whole undefined thing, because that's the answer. That bit there is the answer to a limit. Okay? So as L approaches infinity, what we want to do is the integrand. Now what is this thing here? To do our normal integration, let u equal minus x so for me, that's the thing we're actually substituting. Is that up there? Yep, there it is. So we're putting minus du in. That's the important substitution. Most students doing u substitution integration can't bring me to that point. Okay, that's missing. That important information is missing. They'll do this with glee. Oh, we do this. That's what we do. Yeah, but that's not important. The other stuff is. All of this is important. And then the other thing that we've got to do is check our limits. So when using function notation, this would be minus infinity, and when it's 0 it would be 0. So the only change is the minus infinity. Now there's an ambiguity that takes place. They don't always, where before we had 0, infinity, minus infinity, but the minus takes care of the problem there. So with a shortcut, if you're teaching shortcuts, that's the issue. Okay, so when you're teaching shortcuts, it's to avoid having to cope with the change of limit. Okay, so what we get is minus e, and our minus e to the minus x between L and 0. So I'm assigning these L and 0. So we'll get our limit. Does the limit exist? I might just pop my head out of the way there. Does the limit exist as L approaches infinity? And so we need to then do our scaffolding in the usual way. So we're going to bomb L. So we'll have minus e to the minus L. And then we're going to subtract minus e to the minus 0, or 0. Anything raised to the power 0 is 1, so that's indices again. So we've got minus e to the minus L. Minus times minus is a plus. That guy there is 1. Okay. And what we know is that in checking the limits for this first expression, we can put brackets around that. The limit of 1 will remain 1, and then the limit of this term will disappear. That one will disappear. And that's this in action. That's this part of the curve in action. The limit is effectively becoming 0. Okay. So this is the analysis side of the course. I'm not going to distress you and cause you great pain in this, which is why I've put the high school maths as your micro teach. Anything that we'll do in terms of questions, you'll have an example to work off. It won't stray too far from where you're at, but I need you to be exposed to it. Now, if you haven't done Calculus 2, the limit stuff is missing, and so that's a bit tricky. Okay, but if you want me to go back over it, I can go back over it. It's assumed knowledge for Calculus 3, but I'm happy to go back over it in the first part of the lecture. All right. So what I want to do there is just press pause, because I think that's probably enough of an example. There are examples in. Now, what can we do? Technology to help with that? You're a very naughty boy, Jason. You are a very, very naughty boy. So we're going to integrate. Let's see. I love Mathematica, I've got to tell you. Actually, my PhD's on Mathematica. Well, use of it. I'll have to show you this time. I said I would show you last time, but I didn't. So what do we got? Minus x. And what are we going for? Dx. And then we want x going between 0 and infinity. I think you'll all recognise that. And and I think I said last semester, didn't I, that if you spend a few bucks on a subscription, guess what you'll get? You'll get all the steps. Okay? And that's what we would do by hand anyway. Okay? So there's no embarrassment in giving yourself a bit of help. Okay? As far as I'm concerned. You might have a different opinion, and I'm happy for you to do it by hand using the limits, or not, either way. Okay, but I'm giving you insights into what mathematicians do, because it's part of the course requirement, but also it's important that you have a sense. Now, do you want me to do another example, or are we happy to press pause there? How are you feeling? Enough? Because it was going to be the night of no homework, right? So I've got to be fair. All right, let's pause there then. Are you okay with that? Yeah, we got a couple of nods.
Yeah, I'm okay.
All right, let's pause with that. See what you can come out of with your, but essentially that's the gist of it up there. Okay, I've put some worked examples up there for you to view, and I've done another little video for you, and hopefully that will set you on your path. I hope you're not feeling too intimidated. That's not what I want for you. I'm not brash, I'm not arrogant, I'm trying to be informative. I'm a great believer in training. If you get the training that you need, you will succeed, and you'll be able to do things that will knock your socks off. Alright, let's press pause there, and I'll see you all next week. Please feel free to drop me a line if you need to. I'm happy to have a chat.
Okay, thanks, Jason.
Alright,
Thanks,
see you.
Jason.
See you, Tricia.
Thank
See you,
you.
Cindy.
See you,
Bye.
James. Bye.
Bye-bye.